In this video, we are going to talk about the Fundamental Theorem of Calculus, Part 1. So the Fundamental Theorem of Calculus is a theorem that's going to relate the tangent line problems that we were doing earlier on to the area problems that we've recently been talking about. So it kind of ties together these two distinct pieces of places where limits show up into one related area. And the way we're going to do that is we're going to start by looking at functions of the following form. So we're going to let g of x be defined to be the integral from a to x of f of t dt, where f is a continuous function on some interval a to b, and x is allowed to vary between a and b. And so what we're saying here is graphically, we're saying we have some value a, some value b, and we've got some function y equals f of t that's defined here, and this function g of x is going to give us the area kind of in the middle. And so we start at a and we pick some value x, and then g of x is going to give us the area from a to x underneath the curve. And if we picked some new x, so say some x2 here, it's just going to give us more area. So it's giving us the area under the curve f of t from a up to x, and we let x go anywhere from a up to b in value. So you can think of this as a function that's basically just giving us the area up to a certain point. So the actual area is a fixed number, and those are just our outputs from this function. Now, in reality, this does allow for negatives, so g of x is actually going to give us the net area from a to x under f of t. But I drew it positive in this picture. So let's do an example to get a little bit more of an idea of what this function really is talking about, what functions like this are like. And so if f is the function whose graph is shown below, and g of x is going to be integral from 0 to a of f of t dt, we want to find values of g of x. So we're just going to find different values of this function using the graph that we're going to have below. The reason for this is just kind of to really cement home what this function is really saying. Okay, so I haven't drawn this graph really well, but hopefully it's clear enough what the picture is trying to do that this will make sense. So first we're going to compute g of 0. So g of 0 would be the integral from 0 to 0 of f of t dt. Well, if we're going from 0 to 0, we don't have any area. Okay, we haven't moved anywhere. And so the value is 0. And one way of thinking of this is that when you look at a minus b in like the Riemann sum, your delta t is just going to be 0 because a and b are the same value. You just have 0 minus 0 over n. So you get 0 times something, and so that whole sum will be 0. So let's look at a bit more interesting one. So the integral from 0 to 1 of f of t, this will be g of 1. Well, graphically what that looks like is we're going from 0 to 1, so we've got this triangle. And we've talked about before how we can use areas to compute integrals. So we've got a triangle. The area of a triangle is 1/2 base. The base of this triangle is 1 times the height. The height of our triangle is 2. And so g of 1 is then going to be 1/2 times 1 times 2, which is just 1. So g of 1 is 1 because it's the area from 0 to 1. Continuing on, g of 2 is the integral from 0 to 2 of f of t dt. So now we're going from 0 all the way up to 2. So we're just going to basically add on this next piece. We can think of this as the integral from 0 to 1 of f of t dt plus the integral from 1 to 2 of f of t dt. This is just using properties of integrals that we've talked about before, how you can go part way and then the rest of the way. We already know the integral from 0 to 1 is equal to 1. And from 1 to 2, we just have this rectangle with a base of 1 and a height of 2. So we get 2 from there. And so the g of 2 is going to be 1 plus 2, which is 3. And again, g of 2 is just the area that we've shaded here. It's the area from 0 to 2. So it's the area of this rectangle plus this triangle. So next we'll do g of 3, which is the integral from 0 to 3 of f of t dt, which is the integral from 0 to 2 of f of t dt, plus the integral from 2 to 3. We already did 0 to 2. That was g of 2, so we know that's a value of 3. Now from 2 to 3, we have this piece right here. Now admittedly, I just gave a graph, so we are just going to approximate what that is. And notice that's slightly bigger than a triangle. So if I was to draw a triangle here, notice that I'm getting more area than the triangle. And the triangle has an area of 1. It's the same as the orange triangle I drew before, just on the other side. And so I'm going a little bit above that. And so what we're going to say here is that that is about 1.3. Now, that's an approximation. This is about 1.3. And so we've added it on, and so the area now is 4.3. So g of 3 is going to have a value of 4.3. And again, it's giving us the area of this whole piece above the x-axis that we've drawn so far. Next, we come to g of 4. It's the integral from 0 to 4 of f of t dt, which is the integral from 0 to 3 of f of t dt, plus the integral from 3 to 4 of f of t dt. We know 0 to 3 has a value of 4.3, about. We're, again, rounding. Now, this is where my drawing skills somewhat limit us. But we're going up to 4 here, and so we're sticking on this piece right here. And as I'm not a very good artist, it's not very clear, but these two pieces are supposed to be the same size. That's not very clear because I didn't space things out, but notice this goes up 1, 2, and this goes down to -2. They're supposed to be the same. I'm just not drawing it very well. So we're going to say this has about an area of 1.3 as well. But because it's below the x-axis, we have a negative value. So this piece from 3 to 4 will be negative 1.3. Taking into account we are below the x-axis. And so we get the g of 4 has a value of 3 then, which again, it's the net area from 0 to 4. So we get all of this area above, which was 4.3, and then we have to subtract off that 1.3 from below the x-axis. And then g of 5, is the integral from 0 to 5 of f of t dt, which is the integral from 0 to 4 of f of t dt, plus the integral from 4 to 5 of f of t dt. From 0 to 4, we found a value of 3. So now we want to go from 4 to 5. So in our picture, that's this piece right here. Notice that's below the x-axis, so we're going to treat it as negative. It's supposed to be symmetric to the piece we just did, so this is supposed to be another negative 1.3. So we should get about 1.7. And so g of 5 is 1.7 then. And again, what that's telling us is that's telling us the net area, if I go from 0 over here, up, over, around, and then down, if I take this whole region, the net area from 0 to 5 is going to be 1.7, treating everything above the x-axis as positive and below as negative. And so this function is just telling us the area under the curve up to a certain point. Hopefully that's a bit more clear what these functions actually are doing now. Now you might wonder, where am I ever going to see a function like this? It turns out that these functions have a number of applications. I'm just going to mention one of them, as I'm not going to claim I'm an expert on all of the uses of this. But one such function is called the Fresnel function. I hopefully am pronouncing that right. And so it is s of x, and it's equal to the integral from 0 to x of sine of pi t squared over 2 dt. And so this is a function that is used when you're studying the diffraction of light waves, so like how light diffracts, as well as it's used in designing highways. And I don't actually know how it's used in designing highways. I think it has to do with the sound waves, though, with regards to highways. But this is a function that actually is used in construction and in studying light. And so we do see functions like this. They are things that do show up. Our interest in it will be more with studying a bit more about its algebraic and calculus properties, but it does have applications. And so now, as we just saw from this, it can take kind of a lot of effort to compute all of these areas. Computing definite integrals is not particularly easy. And so it'd be nice if we could actually find a formula without an integral in it for g. And so what we're going to do is we're going to look at kind of the simplest, well, not the simplest example, but a simple example. We're going to look at g of x equals the integral from 0 to x of just t dt. So this function is literally telling us that if I draw the line y equals x, which I guess is going to be y equals t here, this function is literally telling us when I pick some value x, what is the area of this triangle. Again, now I'm letting x range, but it's just computing the area of these triangles. As we get bigger and bigger in x, we're getting bigger and bigger triangles. And we'd like to have a closed form for this that doesn't involve an integral. This one wouldn't be too hard since it's just a triangle, but it's going to motivate our idea for the future. And so the way we're going to do this is we're going to rewrite this integral as a Riemann sum. So this will be the limit as n goes to infinity of the sum from I equals 1 to n. And then we need to find, remember it's f of x sub I. I'm going to use t though here, so it's going to be t sub I delta t. And now delta t is going to be b minus a over n, so it's x minus 0 over n. So we have x over n is our delta t. And our t sub I, our f of t, I guess I should mention, f of t is just literally going to be the function t. That is the function we're taking the integral of, so that's where it's coming from. T sub I, remember, is a plus I delta t. A is 0, and delta t is x over n, so this is going to be ix over n. So that is t sub I, and we're going to plug that into f of t. So what we have here is that g of x is the integral from 0 to x of t dt, which is the limit, then goes to infinity of the sum from I equals 1 to n of f of t sub I. F of t is just t, and t sub I is ix over n, so we're going to have ix over n times delta t, which is x over n. So this is the limit. Then goes to infinity of the sum from I equals 1 to n of I x squared over n. And now we can compute over n squared, Now we can compute this. And so we're taking the sum from I equals 1 to n. So x and n are not really relevant to the sum, so we can pull them out to have the limit. So n goes to infinity of x squared over n squared times the sum from I equals 1 to n of I. We know how to compute the sum from I equals 1 to n of I, though. So this is the limit as n goes to infinity of x squared over n squared times the sum from I equals 1 to n of I is n times n plus 1 over 2. And so we have the limit. So n goes to infinity of x squared n times n plus 1 divided by 2 times n squared. We can cancel an n on the top with an n on the bottom to give us the limit. So n goes to infinity of x squared n plus x squared divided by 2n, which is the limit as n goes to infinity of x squared over 2 plus x squared over 2n. And as n goes to infinity, x squared over 2 is just going to go to x squared over 2, but x squared over 2n will go to 0 because 2 times n will get really big, so that piece goes to 0. Because remember, x is fixed. It's just some fixed number that we're looking at the sum going up to that point. So in the limit, we get x squared over 2. Now at first, you might forget what we were trying to do, but what we found then is g of x, which is the integral from 0 to x of t dt, is equal to x squared over 2. So this gives us a formula that tells us the area of that triangle that we were forming for any x. So rather than computing the area of this triangle every single time, we found that it's just going to be x squared over 2. Now, we admittedly could have just looked at the triangle using x plugged in and found it was also x squared over 2, using the fact it's a triangle. But I thought going through another practice of this sum might be helpful, which is why we did it this way. But another way you could do this is you could say, oh, well, the height of this triangle is going to be x, the base is x, because we're going out to x. And so we're going to have 1/2 times x, which gives us x squared over 2. Okay, so that's another way of doing it. It's much faster than what we just did. But I think practicing computing these limits of Riemann sums is helpful. But what's interesting about this is notice what the derivative of g is. If I take the derivative of x squared over 2, I get 2x over 2, just using the power rule, which is x. So I get out x, which looks an awful lot like t. It's the same function, just with a different variable. And so in other words, g prime is equal to f. So in this case, we found that that g is an antiderivative of f. Well, that's kind of interesting. So the area from 0 up to x proved to be an antiderivative of f in this case. And that got mathematicians wondering, well, is this just a coincidence, or does this always happen? And that's where the first part of the Fundamental Theorem of Calculus comes from. It basically says this isn't a coincidence, but let's write it down. So this is the Fundamental Theorem of Calculus, part 1. There are 2 parts to it. We're only going to talk about part 1 in this video. Part 2 will be in the next video. Now, if f is continuous on a closed interval a to b, then the function g defined by g of x equals the integral from a to x of f of t dt for a less than or equal to x less than or equal to b. So that's just saying that this only works for picking values of x in between a and b. So this function is continuous on the interval a to b and differentiable on the open interval a to b with the derivative of g equal to f of x. Now this last part is probably the part that gets remembered the most. It basically says that if we take the derivative of the integral, we get out the original thing, or in other words, g is an antiderivative of f. Okay, so that is a pretty interesting fact. We are going to prove this. Okay, so we're going to prove the Fundamental Theorem of Calculus Part 1 now. Okay, so first, remember how derivatives are defined. Maybe we should write that down first. So remember that the derivative of g is defined to be the limit as h goes to 0 of g of x plus h minus g of x divided by h. Okay, so that's the definition of the derivative. It's going to come up in the proof like right away, so I thought probably a good idea to remind you. That's why we're kind of shooting for g prime of x being equal to f of x. So that's why we're going to be looking at what we will be in the proof. Okay, so if x and x plus h are in the open interval a to b, then we have the following fact happening. So g of x plus h minus g of x is going to be equal to the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. Okay, so I just plugged them in. This is literally how g is defined. Now we're going to break the first of these up using an integral property. So the integral from a to x plus h is the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt. And then we minus off the integral from a to x of f of t dt. Now notice that the first term here and third term cancel. So I'm just left with the integral from x to x plus h of f of t dt. Okay? Well, that's great. So then that tells us something about the formula that we care about. So remember, what we care about is the limit of g of x plus h minus g of x divided by h. We're going to take the limit of this as h goes to 0, but we just found as long as h is not 0, which in the limit we assume it's not, this equals 1 over h times the integral from x to x plus h of f of t dt. And so if we want to compute the derivative of g, it suffices to take the limit as h goes to 0 of this 1 over h times the integral from x to x plus h of f of t. Okay, so that's what we're going to do next, is we want to compute that limit. Now we're going to kind of do this in, I guess, two parts, you could say. We're going to assume h is positive to start with, but I'm really going to assume h is positive and then mention the negative case almost as an afterthought, because the argument is the same. So we're going to assume h is greater than 0. Okay, and then since f is continuous on the interval from x to x plus h, remember that f is always continuous on a to b, we have by the extreme value theorem says there are numbers u and v in the closed interval x to x plus h, such that f of u is always going to be less than or equal to f of x, which is always less than or equal to f of v, where f of u is the absolute min of f, and f of v is, I said f of x here, but this should be f of t, sorry. And f of v is the absolute max of f on the interval x to x plus h. Now, this might seem like a kind of wordy statement. Literally all this is saying is, because we have a closed interval and a continuous function, we know it has a smallest value and we know it has a largest value. F of u is the smallest value, and f of v is the largest value. Okay, so that is literally all we are saying here with the extreme value theorem. We've got a smallest value, we've got a largest value. Okay. So now by the comparison property, I think it was called the comparison theorem, of integrals, we have that f of u times h must be less than or equal to the integral from x to x plus h of f of t dt, which is less than or equal to f of v times h. Okay, now this is coming from this statement right here that f of u is less than or equal to f of t is less than or equal to f of v. And we talked about this at the end of the definite integral video. So if you don't remember why this is true, you can go back there. But the idea here is that this piece here, the integral from f of u times h, this is equal to the integral from x to x plus h of f of u dt. And this is equal to the integral from x to x plus h of f of v dt. And so we've just basically taken the integral of those two constants on either side. And that's where we get the formula from, just saying basically the area has to be contained between these two since the function always is. But now why we're interested in this is if we divide everything by h, which is positive, so we don't have to flip signs, we get f of u is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to f of v. So I just divided everything in the above formula by h. And so this gives us an equation with relation to the integral from 1 over h times the integral from x to x plus h of f of t dt. Well, now we're going to take the limit as h goes to 0. And so the limit as h goes to 0 from the right, I'm assuming we're positive, that's why it's from the right, of f of u. Well, this piece might be a little bit, and also the limit as h goes to 0 from f of t, of f of v, I mean. Both of these, it helps if you look at a picture just to remember what we're doing here. So remember what u and v actually were. And so if we have a picture, I'm just drawing a random function for f, just for drawing purposes. So when we say x is right here, and then x plus h is somewhere over here. Now f of u, remember, u was found to be where the minimum occurs. So u is like right here, and v is actually probably the same as x plus h in this picture. But as h goes towards 0, we're going to be shrinking this down. And so we're going to be collapsing this interval, and it's getting smaller and smaller. And so in some sense, u and v, which are the x coordinates for the minimum and max, are going to get collapsed down on top of x, because we're going to be shrinking down the picture. And so we'll see if I can draw the same thing. So now we're saying like x is right here where it was before, but now all of a sudden I've made x plus h like right here. I've made h smaller, so I've compressed things. Well, now where are u and v? Well, in this case, v actually is the same as x now, and u is the same as x plus h. But as I keep pushing them closer and closer, they're both going to collapse down on x. And so because of that, f of u is going to end up being f of x, and f of v is going to be f of x. It's just this idea that we're just kind of collapsing down everything by sliding h to closer and closer to x, so that the min and max have to both happen right at x in the limit. Okay? And so now, why this is interesting to us is we have that f of u is less than or equal to the integral from x to x 1 over h times the integral from x to x plus h of f of t dt is less than or equal to f of v. And we just computed the limit of f of u is f of x, and the limit of f of v is f of x. And so by a theorem that you very well might have forgotten exists, we have by the squeeze theorem that the limit, as h goes to 0 from the right, of 1 over h, the integral from x to x plus h of f of t dt, must equal f of x. Okay, so the limit from the right by the squeeze theorem has to be f of x. So that handles all of the positive cases. Now we're going to go through and talk about the negative case when h is less than 0. And it proves to be almost the exact same. Okay, so now we're going to consider the case when h is less than 0. And it's going to be very similar, so I'm just going to write the changes in red. So we're having h is less than 0. So now instead of going from x to x plus h, we're going to actually go from x plus h to x. Okay, and so this is just basically kind of we have to change things a little bit because h is now negative, so x plus h is actually to the left rather than to the right. So our interval is now x plus h to x. All of the stuff with the extreme value theorem is still true. We still can find a u and a v. And now we still want to, going to take the integral from, in this case, x plus h to x. And so this piece right here will get changed somewhat. So now we'll take the integral. In the middle, I guess, is the easiest part for us. So it's going to be x plus h to x of f of t dt. Because now x plus h is on the bottom, so that's on the bottom. This piece gets changed to be the integral from x plus h to x of f of u du, which is going to be equal to f of u times x minus x plus h. And so we're going to end up with, in this case, negative h times f of u. And on this side, we get negative h times f of v. So it's basically the same. It's just that we now have a negative h. We have negative h times f of u is less than or equal to the integral from x plus h to x of f of t dt is less than or equal to negative h times f of v. Now I'm going to divide everything by negative h. Remember, h is negative, so negative h is actually positive. So we're going to get f of u is less than or equal to 1 over negative h, the integral from x plus h to x, f of t dt is less than or equal to f of v. But remember, we can switch the bounds by pulling a negative out. And so we'd have the f of u then is less than or equal to 1 over h times the integral from x to x plus h of f of t dt is less than or equal to f of v. And from this point, the argument for h less than 0 is the exact same. So we'd still compute the limits. Now we take the limit as h goes to 0 from the left rather than the right. But all of the argument from this point on follows the exact same way to get the limit as h goes to 0 from the left of 1 over h times the integral from x to x plus h of f of t dt equals f of x. I know I kind of skipped over that, but it's basically the exact same argument. You just have to pay attention to the negative. So what that then gives us is that the limit from both the left and the right are equal. So the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to f of x. But remember that we found all the way up here this relationship, that 1 over h times the integral from x to x plus h of f of t dt is equal to g of x plus h minus g of x over h. And so plugging that in, we have the limit as h goes to 0 of g of x plus h minus g of x divided by h equals f of x. But now that's the derivative of g, so g prime of x equals f of x. And that then is the proof of the first part of the Fundamental Theorem of Calculus. Now we want to actually use the Fundamental Theorem of Calculus to do some examples. So let's go through some examples of actually making use of it, just to kind of make clear what we were doing. Okay, so first off, in Leibniz notation, the Fundamental Theorem of Calculus literally just is saying the derivative with respect to x of the integral from a to x of f of t dt equals f of x. So it's basically saying the derivative of an integral is the integrand. Okay, so they like undo each other in this order when you do the derivative of an integral. That's what the Fundamental Theorem of Calculus Part 1 basically is saying. It's a little bit more complicated than that, but that's the general idea for it. So now let's look at an example. And so we want to find the derivative of g of x equals the integral from 0 to x of the square root of 1 plus t squared dt. Okay. Well, by the Fundamental Theorem of Calculus, we can do this very quickly. And so I'm just going to write Fundamental Theorem of Calculus Part 1. So the Fundamental Theorem of Calculus Part 1 tells us that the derivative of g is literally just x plugged into this. So it's just going to be the integrand with t replaced by x, so it's the square root of 1 plus x squared. So that's literally what the Fundamental Theorem of Calculus is telling us. It's telling us since f is a continuous function, since this function, square root of 1 plus t squared, is continuous, that it's the derivative of the integral from 0 to x of the square root of 1 plus t squared is just the square root of 1 plus x squared. Okay, so basically we're saying the derivative of the integral from 0 to x of the square root of 1 plus t squared dt equals the square root of 1 plus x squared. Okay, I'm not going to belay this point any further. Hopefully this is making sense. Now the interesting part comes when our x is not in the top. And so next, we want to take the derivative of the integral from x to negative 3 of 4t plus 5 dt. Okay, the Fundamental Theorem of Calculus does have the x in the top position, and that is relevant to the theorem. And so before we can apply the Fundamental Theorem of Calculus, we need x to be the top bound. But we actually know how to do that very easily. This is just equal to the derivative of negative the integral from negative 3 to x of 4t plus 5. Remember that you can flip the bounds by just pulling out a negative. Negatives can be pulled out of derivatives, so this is negative times the derivative with respect to x of the integral from negative 3 to x of 4t plus 5 dt. And now we can use the Fundamental Theorem of Calculus Part 1 to take that derivative. So we get negative times 4x plus 5. Multiply the negative in, so we get negative 4x minus 5. And so that is our derivative. So when your x is in the bottom position, you first need to flip it so it's in the top position, and then you can apply the Fundamental Theorem of Calculus. Part 1. We'll talk about Part 2 again in the future. Okay, next. Now we want to find the derivative with respect to x of the integral from 1 to x to the 4th of secant of t. Okay. So now this one actually is a little bit more limiting to us, as now we have x to the 4th in the top. And remember that I said we need x to be in the top. Well, by x in the top, I mean we literally need the variable x. Whatever variable we're taking the derivative with respect to, which is x here, that has to be the top bound to use the Fundamental Theorem of Calculus. And right now it is not. And so what we're going to do here is we're actually going to do a chain rule. Okay, so we're going to think of this as a composition of functions. And so here, our outer function is the integral from 1 to x of secant of t dt. And our inner function, which I'll write as g of x, is x to the 4th. Notice that I have plugged x to the 4th in for x and g of x. So just to make it clear, f of g of x. Wherever I see an x in the formula for f, I need to plug in x to the 4th. Well, I only see it in the bound, so I have 1 to x to the 4th secant of t dt. So the composition of these functions is the thing I wanted the derivative of. And so now we just need to use the chain rule. And so the chain rule says we take the derivative of the outer function, evaluate it the inner function, times the inner function. Okay, well, what is the derivative of the outer function? Well, the outer function's derivative is, we're taking the derivative from 1 to x of secant of t. Well, the Fundamental Theorem of Calculus tells us that's just secant of x. So f prime of x is just secant of x, and g prime is easy enough to compute, it's just 4x cubed. And so now the derivative, using the chain rule, of the integral from 1 to x to the 4th of secant of t dt is equal to the derivative of the outer function, evaluated the inner function. The inner function is x to the 4th, so we have secant of x to the 4th. This is f prime of g of x. I'll write that in a different color. So this is f prime of g of x. And then I multiply that by g prime, which is 4x cubed. And this is g prime of x. And so we've just used the chain rule to get that the derivative is 4x cubed secant of x to the 4th. And again, we had to use the chain rule here because the Fundamental Theorem of Calculus only applies when the thing we're taking the derivative with respect to is in the upper bound. And by the thing we're taking the derivative with respect to, it has to be that exact variable. Okay, so let's look at one more example just to make this clear. Okay, so what we have here is if f of x equals the integral from 0 to cosine of x of t cubed plus 3 dt, and g of y equals the integral from 4 to y of f of x dx, we want to find g double prime of y. Okay, so in other words, we're taking the second derivative of g. Well, to take the second derivative, we have to take the first derivative. So first we want g prime of y, which is the derivative with respect to y of the integral from 4 to y of f of x dx. I'm just going to write f of x. F of x is itself an integral. It's this integral. So really what we're looking at here is the derivative with respect to y of the integral from 4 to y of the integral from 0 to cosine of x t cubed plus 3 dt dx. Okay, but that looks kind of complicated, so we're not going to think of it that way. We're just going to view it in this way. Okay, and so notice though that y is both the variable we're taking the derivative with respect to and the upper bound. So by the Fundamental Theorem of Calculus Part 1, g prime of y is just equal to f of y. Okay, and so we've got that g prime is just equal to f of y, which is great. Now we just need its second derivative, which again, f of y would then be the integral from 0 to cosine of y t cubed plus 3 dt. Okay, I've replaced the x with a y because now it's f of y rather than f of x. But it's the same idea. Okay, so now we need to take the second derivative because we want g double prime. And so g double prime of y is going to be the derivative with respect to y of the integral from 0 to cosine of y of t cubed plus 3 dt. Well, now to do this, we're going to have to use the chain rule again. Our outer function is going to be the integral from 0 to y of t cubed plus 3 dt. And our inner function is just cosine of y. The derivative of the outer function using the Fundamental Theorem of Calculus, Part 1, is just going to be y cubed plus 3. And the derivative of cosine is negative sine. Okay, and so using the chain rule then, we have that the derivative with respect to y of the integral from 0 to cosine of y of t cubed plus 3 dt is equal to the derivative of the outer function with the inner function plugged in. So we're going to have cosine cubed of y plus 3. I've plugged the cosine into the inner function. And again, this is f prime of g of x. Technically, I'm using f and g differently here, but this is the derivative of the outer function, the inner function plugged in, times the derivative of the inner function, which is negative sine of y. And so we then have that g double prime of y is equal to negative sine of y times cosine cubed of y plus 3. And so that is then our second derivative. And so hopefully this makes sense on the first part of the Fundamental Theorem of Calculus. We will talk about the second part of the Fundamental Theorem of Calculus next time.